One day, the universe is going to end. Not soon, not in any span of time a human mind can hold. But it will end, and for the last 30 years we have believed we knew exactly how. It ends in cold. The galaxies drift apart from one another, slowly, patiently, forever. The last stars burn through the last of their fuel and go out. The gas that might have made new ones is spread too thin to gather. Black holes swallow what is left, and then, over spans of time so vast the numbers stop meaning anything. Even they evaporate away into nothing. And what remains is dark, and it is cold, and it is empty, and it stays that way for the rest of time. It is a bleak ending, but it is a settled one. It is in the textbooks. It is what your children are taught. It is the consensus of the entire field, built on a discovery so important that the 3 men who made it were given the Nobel Prize in physics. And in the last 2 years, the largest map of the universe ever made has begun to suggest that it might be wrong. Not wrong in a detail, not wrong at the edges, wrong about the thing that decides how everything ends. This is the story of a number that was supposed to be a constant, of the instrument built to measure it precisely, which instead found that it might be moving, and of 900 scientists who finished the job they set out to do, looked at what they had found, and decided they could not walk away from it, because it will not go away. To understand what is cracking, you have to go back to the last time this happened, the late 1990s. 2 teams of astronomers, working separately, in quiet competition with one another, set out to measure something that almost nobody thought was in question. The universe had been expanding since the Big Bang. Everyone agreed on that. Galaxies were flying apart from one another and had been for billions of years. But gravity is patient, and gravity pulls, and across all that matter it should have been quietly applying the brakes. The expansion should have been slowing down. The only real question was how much. Whether the universe would eventually stop and fall back in on itself, or whether it would coast outward forever, slowing all the while, but never quite stopping. To find out, both teams went looking for exploding stars, a particular kind called a Type 1a supernova. These matter because they are predictable. When a certain type of dead star takes on too much mass, it detonates. And it detonates at very nearly the same brightness every time, which means that if you find one and it looks dim, you know how far away it is. They are candles laid out across the depths of space, and by measuring how bright they are, you can measure the shape of time. The teams found their supernovae. They measured them, and the numbers came back wrong. The distant explosions were too faint. Not by a great deal, but unmistakably. And in cosmology, a star that is dimmer than it should be is a star that is further away than it should be. Which means the universe had not been slowing down at all. It had been speeding up. Something was pushing the universe apart. Something that had been getting stronger, not weaker, across billions of years. Something that nobody had asked for, nobody had predicted, and nobody could explain. The astronomers did not believe it. That is the part that matters, and it is the part that usually gets left out. They did not run to announce it. They assumed they had made a mistake and they went looking for it. They checked their calibrations. They checked their dust corrections. They checked each other. And the more they checked, the more the result refused to go away. So they published it. And the universe we thought we lived in stopped existing. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe. It is one of the great results of the last century. It is the moment we found out that most of the universe is made of something we cannot see, cannot touch, and cannot explain. They called it dark energy. And the name is not an answer, it is an admission. It is what you write on the box when you know something is in there and you have absolutely no idea what. Here is what we know about it, and it is not much. It is not matter. It does not clump, it does not gather, it does not fall together under gravity the way everything else does. It appears to be spread perfectly evenly through all of space. And unlike everything else in the universe, it does not thin out as space expands. Make more space and you get more of it. That is the strangest property of dark energy, and it is worth sitting with for a moment. Take a box of gas and double the size of the box, and the gas gets thinner. Take a region of the universe and double its size, and the amount of dark energy in it doubles too. It is not filling space. It appears to be a property of space itself, of nothing, of the vacuum. And because there is more nothing every year, there is more of it pushing every year, and the expansion accelerates. That is the engine that ends the universe. The simplest way to write that idea down in the mathematics is as a constant. A single fixed number, the same everywhere, the same always. It even has a symbol, the Greek letter lambda. And there is a story attached to lambda that is almost too neat. In 1917, Albert Einstein was working through what his own equations said about the universe, and he did not like the answer. The mathematics insisted that the universe must be either expanding or collapsing. It could not simply sit there. And in 1917, everybody knew that the universe simply sat there. So he added a term, a fudge, a constant tuned by hand to hold the universe still. "12 years later, Edwin Hubble looked through a telescope and showed that the universe is expanding after all. Einstein had been right the first time and had talked himself out of it. He removed the term, and he is said to have called it the biggest blunder of his life. And then, 70 years after that, 3 astronomers found dark energy and reached back into the waste paper basket and pulled his blunder out of it. The constant Einstein invented for the wrong reason turned out to be needed for a reason he could never have imagined. So the model was assembled, and it was given a name that sounds like a filing code, because that is what physicists do. Lambda-CDM. Lambda for the cosmological constant. CDM for cold dark matter, which is the other invisible thing, the one that holds galaxies together. And that model is not a fringe idea. It is the foundation. It is how we calculate the age of the universe. It is how we explain the way galaxies formed and clustered. It is how we read the faint afterglow of the Big Bang itself. Nearly everything modern cosmology says about anything rests on it. And here is what it says the universe is made of. Roughly 68% of everything is dark energy. Roughly 27% is dark matter, which leaves the ordinary stuff, the atoms. Every star you have ever seen, every planet, every ocean, every living thing, every object you have ever touched or will ever touch. 5%. We built the most successful model in the history of physics, and 95% of it is a name we gave to something we have never found. And still, it worked. Every measurement we made came back consistent with lambda being a constant, and the ending it implied, the cold, the dark, the long, slow fade, settled into the textbooks as simply the way things are. Except for one thing. One enormous, embarrassing thing, which physicists mostly do not talk about in public. If dark energy really is the energy of empty space, then we ought to be able to calculate it. Quantum field theory says the vacuum is not empty at all. It seethes with particles flickering in and out of existence, borrowing energy and giving it back. That activity has an energy, and that energy should push space apart. So physicists calculated what it should be. The number they got is too big. Not by a factor of 2, not by a factor of 1,000. It is too big by a factor of 10 to the power of 120. That is a 1, followed by 120 zeros. There is no analogy that helps. It is routinely described as the worst theoretical prediction in the history of physics. And that is not a joke made by critics. It is what the physicists call it themselves. So we have a model that works beautifully, that predicts the sky with extraordinary precision, and at the center of it sits a number we cannot derive, cannot explain, and cannot even get within 120 orders of magnitude of. We simply measure it, write it down, and move on. To be certain, though, you have to measure it properly. Not once, not with a few dozen exploding stars. You have to watch dark energy across the whole history of the universe and see whether the number holds. Which is why they built DESI. On a mountain in Arizona, on a telescope that has been staring at the sky since the 1970s, they installed something extraordinary. 5,000 robotic eyes. Each one is a tiny positioner holding a fiber optic cable, and each one can be aimed independently. Every 20 minutes, all 5,000 of them swing to a new set of targets, and they do it with a precision of about 1/10 of the width of a human hair. 5,000 galaxies at a time. Then another 5,000, then another. Night after night, for 5 years. The Dark Energy Spectroscopic Instrument does not take pictures. It takes spectra. It splits the light of each galaxy into its colours, and from the way that light has been stretched on its journey, it works out how far away that galaxy is and how fast it is moving away from us. Do that enough times, and you are not looking at a photograph of the sky, you are building a map in 3 dimensions of the universe. And to measure the shape of that map, DESI uses one of the strangest rulers in science. In the first 400,000 years after the Big Bang, the universe was too hot for atoms to form. It was a plasma, and sound waves rippled through it, spreading outward in shells from every dense point. When the universe finally cooled enough for atoms to hold together, those waves froze in place, leaving a faint preferred distance stamped into the distribution of matter. That distance is about 480 million light-years, and it is still there. Galaxies today are very slightly more likely to sit that far apart than any other distance. It is an echo. A sound wave from the beginning of everything, frozen into the arrangement of the galaxies. And because we know how long that ruler is, we can measure how it has been stretched at different distances, at different points in the history of the universe. Which means we can watch how the expansion has changed over time. Which means we can watch dark energy. And it should be a constant. DESI ran for 5 years. In April of this year, it completed the survey it was built to perform. 47 million galaxies and quasars, spanning 11 billion years of cosmic history. The largest 3-dimensional map of the universe ever created, by a wide margin. It was built to pin dark energy down, to take the number that Perlmutter, Schmidt and Rees had found and measure it to a precision nobody had ever managed, and settle the question for good. It did not settle it. The data suggest that dark energy may have been stronger in the past than it is now, that its grip on the universe may be loosening, that the constant may not be constant. There is a number that captures this, and physicists call it W. It describes how dark energy behaves as space expands. If dark energy is a true cosmological constant, if it is a fixed property of the vacuum, as Einstein's lambda would have it, then W is exactly -1. Not approximately, exactly. It does not drift, it does not wobble, it does not change with time. DESI's map suggests W may not be -1, and worse, that it may not be sitting still. I want to be careful here, because this is exactly the point where a story like this usually stops being honest. DESI's data on its own is still consistent with the old model. Taken alone, it does not break anything. The crack only opens when you combine DESI with other measurements. The afterglow of the Big Bang, the exploding stars, the way distant light is bent by gravity as it travels. Fold those together and the picture shifts. Several independent datasets, each of them fine on its own, stop fitting together comfortably unless you allow dark energy to change. And combining datasets is precisely where errors like to hide. It has not reached what physicists call 5 sigma, the threshold at which a result is treated as a discovery rather than a hint. It might still be a systematic error nobody has spotted. It might be something about the supernovae themselves. It might close. But it is not closed. It has grown. And it is not the only crack. There is a second one, and it has been widening for a decade. It is called the Hubble tension, and it is this. There are 2 ways to measure how fast the universe is expanding today. You can measure it directly by looking at nearby exploding stars and pulsating stars and building a ladder of distances out into space. Or you can measure it indirectly by reading the afterglow of the Big Bang and using the standard model to calculate what the expansion rate ought to be now. Both methods are excellent. Both have been refined for years by careful people. And they disagree. Not by much. By around 8%. But the error bars have been shrinking, and the gap has not. And the disagreement is now far larger than either measurement's uncertainty can excuse. The astronomer who has spent the last decade sharpening the direct measurement and refusing to make the discrepancy go away is a man named Adam Rees. The same Adam Rees who found dark energy. The same Adam Rees who won the Nobel Prize. He has now spent half his career discovering that the model he helped build does not quite fit. The first DESI results hinted at it. The second analysis, with more than double the data, hinted at it more strongly. The words the researchers have used are careful, and they are also unmistakable. That the simplest explanation for what they are seeing is shifting. That the standard model of cosmology may not be the best explanation anymore. And then they did something that tells you more than any quotation could. DESI finished the 5-year mission it was designed and funded to perform. It completed the map. And instead of stopping, the collaboration extended the survey to 2028. 900 researchers across 70 institutions looked at a result that will not resolve and decided they could not leave it alone. So what would it actually mean if the constant is not constant? It would mean that dark energy is not a fixed property of empty space. It would mean it is something else. A field spread through the universe with a value that can change over time. Physicists have a name ready for that idea. They call it quintessence, after the 5th element of the ancient philosophers. But a name is not an explanation, and nobody has found the thing the name refers to. It would mean the lambda in Lambda-CDM is wrong. And Lambda-CDM is the scaffolding under nearly everything we say about the universe. And it would mean we no longer know how this ends. Because the big freeze, the long, cold fade, the ending we have all quietly accepted, depends entirely on dark energy staying strong. It depends on the push continuing forever, on the acceleration never letting up, on the galaxies being carried apart from one another, until every sky is empty. Take that away, and every other ending comes back onto the table. If dark energy weakens, the expansion could slow. If it weakens enough, the expansion could stop. And if it were to reverse, if the push were to become a pull, then everything that has been flying apart for 13.8 billion years would begin, slowly, to fall back together. The galaxies would come back. The sky would grow brighter, and then hotter, and then unbearable. And in the end, everything that has ever existed would be compressed back into the single burning point it came from. They call that a big crunch. It was the leading theory before 1998, and dark energy killed it. It is not dead now. And there is a third possibility, which is worse than either. If W turns out to be less than -1, if dark energy is not just changing, but growing more aggressive, then the push does not merely continue, it intensifies without limit. First, the galaxy clusters are pulled apart. Then the galaxies themselves come undone, their stars scattered. Then solar systems unbind, planets drifting away from their suns. Then stars and planets are torn apart from within, and in the final moments, space expands so violently that it pulls apart the atoms themselves. Physicists call it the Big Rip. It is not the leading model, but it is inside the range of values the data currently allows. And it was not 20 years ago. I want to be plain about the level of uncertainty here, because it matters. Nobody is announcing that the universe will collapse. The data does not say that. What the data says is far more unsettling and far more honest. It says we do not know which ending we are living in. And we may not have to wait long to find out. DESI keeps observing until 2028. The Vera Rubin Observatory in Chile has begun a survey that will find more supernovae than every previous survey in history combined. Euclid is mapping the shape of the sky from orbit. The Roman Space Telescope will follow. Within about 5 years, we will either watch this crack widen into a break, or watch it close and go back to the cold. Either answer would be extraordinary. One of them would mean that the most decorated result in modern cosmology needs rewriting. The other would mean the universe really does end in an infinite, silent dark, and that we were right about it all along. I am not sure which of those is more frightening. There is something worth noticing in all of this, and it is not about dark energy at all. Twice now, the universe has been settled. In 1917, everyone knew it was static, and Einstein bent his own equations to agree with them. In the 1990s, everyone knew it was slowing down, and 2 teams went out to measure by how much. Both times, the consensus was not overturned by a theory. It was overturned by somebody bothering to measure carefully, and then being honest about what came back. The astronomers who found dark energy did not want to find it. They spent months trying to make it disappear. The researchers looking at DESI's map are not celebrating. They are being cautious and hedged and slow, and they are extending the mission because they cannot make the result behave. That is not science failing. That is the only part of it that has ever worked. The uncomfortable thing is not that they might be wrong. It is how completely we believed them. The Big Freeze was not presented to us as a hypothesis. It was told to us as a fact. It is in the documentaries and the classrooms and the diagrams on the wall. And almost none of the people who repeat it have any idea that the number it rests on is currently being questioned by the largest survey ever conducted. We are always living inside a picture of the universe that is about to change. We just never know which part of it is about to go. And here is the thing about dark energy that makes all of this feel less like astronomy and more like something closer to home. It is not far away. Dark energy is not out at the edge of the observable universe. It is not something happening to distant galaxies. If it is a property of empty space, then it is a property of all empty space, which means it is here. It is in the room you are sitting in. It is in the space between your hands. It is in the gaps between the letters on this screen, and in every cubic centimetre of the nothing that surrounds you right now, quietly pushing outward, doing the thing that will decide the fate of every star that will ever exist. 68% of everything that exists. In the room with you. Unexplained. And for the first time in 30 years, when we look up and ask how it all ends, the only honest answer we have is that we no longer know.